this videotape, we're going to look at various schemes which are used to protect buses. We all know that the bus is a very important part of the power system, as it must be used at every junction point of lines and feeders. Normally, a bus will have several power sources feeding in and several lines feeding out of the bus. The most simple arrangement would be, for example, at a generation station where, say, 2 generators feed into the common bus and 2 transmission lines transfer the power out of the bus into the system. Invariably, a high-voltage bus is constructed in the open air and consists of aluminum tubes like this. Air provides the insulation between the conductors. At various points along the bus, transmission lines or other circuits are connected through circuit breakers. Disconnects are provided on either side of the breaker so that it can be isolated for maintenance. At lower voltages, the bus may consist of solid copper bars running inside metal-clad enclosed switchgear, which may be built indoors or outdoors. In this arrangement, breakers can be disconnected from the bus in order to isolate them. Common types of faults that can occur on a bus are 1, animals or birds bridging across an insulator to ground; 2, in outdoor substations, lightning flashover, perhaps leading to insulator breakdown; and 3, flying objects bridging across the bus bars. In actual fact, faults rarely occur on buses, but if a fault does occur, then it must be cleared as quickly as possible because of the potential for extensive damage to equipment. Why is this especially so for a bus? Well, look at our simple example. We have 2 close-by generators feeding into the bus and 2 transmission lines taking power from the bus and feeding into the system. If, say, a ground fault occurs on the bus, then we have not only the generators feeding into the fault, but also the power system. The current flow in the transmission lines would reverse and feed into the faulted bus. With such high fault capacity available, the resultant damage could cause a prolonged outage for repair, with the consequent loss of availability of generation and the 2 transmission lines. The direction of current flow forms the basis of bus protection. Using CTs on the outboard side of the circuit breakers like this, we can measure the total flow of current into and out of the bus. If there is no fault on the bus, then the sum of the currents leaving is equal to the sum of the currents entering. The total is 0. Even if there is a fault on one of the transmission lines downstream, the sum of the currents is still 0, as the total current entering the bus is matched by that leaving. The downstream fault would be cleared by other protection relays activated by the inboard CT here. If a fault does occur on the bus itself, the sum of the currents in and out of the bus will no longer be 0. This will cause the protection relays to operate and trip all the breakers connected to the bus. This is the well-known differential principle that we're all familiar with. The principle is simple, but in practice, as I'm sure you'd guess, it's not as easy as all that. And various schemes have been developed to provide adequate bus protection. We'll be looking at these protection schemes in a moment, but first, let's take a look at the different types of bus arrangements you'll come across around the power system. The most simple is this single bus arrangement. The protected zone can be shown by this area, which extends to the outboard bus protection CTs. The inboard CT in each case is used for protection of the connected circuit. For example, in the case of an incoming generator, this CT may be connected to the generator differential. For a transmission line, this CT may be part of overcurrent or distance relay protection. The CTs are usually located in the circuit breaker bushings. To simplify, the following diagrams will show the breaker disconnects in the closed position unless they are normally open. Where a voltage signal is required for protection, say a directional relay or impedance relay, then the VT is normally connected directly to the bus like this. Now, one disadvantage of the single bus arrangement is that any prolonged defect on the bus would necessitate shutting down the whole power station and losing the output from the two generators. In an attempt to improve reliability, the bus is sometimes split with a tie breaker connecting the two halves. In this arrangement, the tie breaker will normally be closed in order to increase system reliability. However, each side of the bus, including the tie breaker, is protected by separate relays. For example, the protection zone of bus B encloses this area. A fault occurring on bus B would cause the connected circuit breakers, including the tie breaker, to open. This would isolate the faulty half of the bus, but leave the remaining section, that is, bus A, to operate intact. As there is only one circuit breaker in each circuit, the line has to be taken out of service when the breaker needs to be isolated for maintenance. One economical way of getting around this problem is to provide a transfer bus. The circuit disconnects are arranged so that any line can feed into either the main bus through the circuit breaker like this, or directly onto the transfer bus like this. Now, suppose that we need to isolate circuit breaker number 1 for maintenance. In this situation, the line 1 disconnect will be connected to the transfer bus, and the tie breaker would now operate as the breaker for that line. So, for the price of one extra breaker, we can substitute any one of the line breakers. While in this configuration, the transfer bus acts as part of the line and is thus protected by the line protection. The inboard CT of the bus tie breaker becomes part of the line protection. This could pose a problem where different protection settings are required for different transmission lines. There is always the possibility of forgetting to make the change or perhaps making incorrect settings. Only the main bus is protected by differential. As shown here, the zone includes the outboard CT of the bus tie. Actually, the transfer bus is not a true bus in that it is never connected to more than one circuit at a time. With a true double bus arrangement like this, both buses A and B are connected to multiple circuits. The essence of this arrangement is that each circuit can be connected to either bus A or bus B, according to the selection of the circuit disconnects. For example, here we show lines 1 and 2 connected to bus A, while the other two lines 3 and 4 are connected to bus B through appropriate disconnects. For simplicity, we are showing only 2 lines connected to each bus. In practice, there would probably be many more. Differential protection is provided separately for each bus. For example, for bus A, the protected zone will include all of this area. The protected zone for bus B includes this area. Incidentally, these diagrams are all included in your workbook to allow you plenty of time to study the different arrangements. In order to provide more flexibility, this configuration allows us to remove a breaker from service without interruption. For example, let's say we wish to remove breaker number 1 on circuit 1. All of the remaining circuits would now be connected to the B bus. The bus tie breaker would now connect bus B to bus A, which now becomes the transfer bus. The bypass disconnect on breaker 1 would now be closed, the breaker opened, and disconnects opened so as to isolate the breaker for maintenance. The transfer bus is connected to only one circuit. Note, before closing the transfer breaker, differential protection on both buses must be disabled, as there may be a current unbalance. As previously mentioned, bus tie protection must be adaptable to all lines. It is apparent that with all bus arrangements, the designer tries to keep the number of circuit breakers to a minimum. After all, these are expensive pieces of equipment. But where the greatest flexibility is required on an important substation, we may find the double breaker, double bus arrangement like this. Each incoming circuit has 2 circuit breakers, thus allowing it to be immediately connected to either bus A or bus B. Each bus has its own differential zone of protection. Now, a fault occurring on, say, bus A will trip all of the breakers connected to that bus and immediately close the breakers to connect these circuits to bus B. With this arrangement, it is necessary to provide 2 CTs for line protection, 1 on each alternate breaker connected in parallel. At the same time, the VTs will be connected 1 to each line. Actually, these junction points fall outside of the bus zone of protection, but they are protected as part of the line protection. A more economical version of this bus arrangement is the so-called breaker and a half. For simplicity, we show just 2 incoming circuits here. You can see that they share the middle breaker, hence the term breaker and a half. Normally, the shared breaker is closed, and both line 3 and line 4 are fed by the 2 buses operating in parallel. You will observe that CTs are installed on all breakers so that both differential and line protection can be provided. Line relays are served by the outboard CTs of the line breakers. Bus differential relays are served by the outboard CTs of the bus breakers. If breaker 4 needs to be removed for maintenance, then simply open and isolate breaker 4. Lines 3 and 4 will now both be fed by bus A. Separate differential bus protection is provided for bus A and bus B. If a fault occurs on bus A, all A-side breakers will open, and since the shared breakers are normally closed, all lines are connected to bus B. The mid-bus sections are protected by the line protection. Another bus arrangement commonly used is the ring bus, like this. Here we have 4 circuits connected to a common ring, which in turn is broken into 4 sections by 4 circuit breakers. A fault on any line will cause the tripping of the 2 breakers on either side. For line protection, the CTs at either breaker must be connected in parallel, like this. This also provides protection for this section of the bus. Voltage for protection must be provided from VTs on each line or each section of the bus. With this arrangement, special bus protection is not required. If a circuit breaker is removed for maintenance, the bus still remains connected to the 4 circuits, but it is now an open bus. However, in this situation, if a fault occurs on one line, then the bus will be split as additional breakers open. Sometimes a circuit may be connected to a bus directly through a transformer. That is, there is no breaker between the transformer and the bus. In this case, the bus zone protection is extended to include the breaker and outboard CT on the primary side of the transformer. A fault on the bus or in the transformer will operate the bus protection to trip all the connected breakers, including the transformer primary. Alternately, separate protection could be installed on both the bus and the transformer. Transformer faults would trip all of the breakers as before. Then a motor-operated disconnect switch could be opened and the bus put back into service. Please switch off the tape and review this material in your workbook. type of differential protection installed depends very much upon the size and importance of the bus in the power system. Obviously, a large, high-voltage substation which interconnects many transmission lines would have far more sophisticated bus protection than a distribution substation. For example, here is a very simple arrangement that is typically used in a distribution substation. The buses are fed from 2 separate sources and feed 8 outgoing radial feeders. As the feeders are radial, the current will not reverse in the case of a bus fault. On this particular system, the bus tie is normally closed. Partial differential protection for bus 1 is provided by the time over current relay 51 connected to these 2 CTs, which are in parallel. If a bus fault occurs on bus 2, a heavy fault current will flow from source 1 into bus 1 and through the tiebreaker into bus 2. The CT currents will be subtractive and therefore will not operate the overcurrent relay. Of course, the CT currents will not be identical because there is some current being supplied to the feeders. The setting of the relay must take this into account. Now, if a fault occurs on bus 1, then heavy fault current will flow into bus 1 from source 1 and also through the tiebreaker from source 2. The current in the 2 CTs will now be additive and consequently will cause the overcurrent relay to operate. This protection will also operate for a heavy fault on a bus 1 feeder, which fails to be cleared by its own breaker. The system therefore operates as backup, and the setting of the relay must allow for this. Of course, a similar pair of CTs will be connected to provide partial differential protection for bus 2. Often, distribution buses are located inside metal-clad switchgear, which may be indoors or outdoors. With this arrangement, you may come across a type of bus protection known as the ground fault bus. This protection scheme is based on the idea that 99% of the faults on the enclosed bus will be to ground, that is, to the metallic structure. Where fault bus ground protection is used, all of the metallic structure and its supports are insulated from ground. One ground connection only is provided, and this passes through a CT. The CT operates an overcurrent relay. Now, if a ground fault does occur on the bus, the fault current will flow down to ground through the CT and so operate the overcurrent relay. One problem with this method is that stray ground currents can cause inadvertent operation of the relay. One way to avoid this is by fitting a supervisory contact in the overcurrent relay tripping circuit. The supervisory relay is controlled by a CT in the system neutral ground. If the ground current through the CT is not due to a system fault, then there will be no flow of current in the system neutral, and the supervisory contact will be held open. However, the biggest disadvantage with this scheme is the possible danger to personnel in the vicinity of the switchgear housing. For example, if a heavy fault current flows through the ground connection, it may raise the voltage on the switchgear metallic housing to a dangerously high level. This could also damage relay, meter, and control circuits connected to the switchgear. For these reasons, this method of protection is rarely used today. The simplest method of providing differential protection is to fit CTs to measure the current in all circuits connected to the bus. In this example, we show one phase only of each line. The secondary side of the CTs are all connected in parallel, and the residual current, that is the current difference, passes through an overcurrent relay. If the current in and out is balanced, then the residual sum of the secondary currents in the CTs is 0. If there is a fault on the bus, then probably all of the circuits will feed into the bus. The current in the CT secondaries will now be additive, and the resulting residual current will operate the time overcurrent relay. Radially connected feeders will not backfeed into the bus, but there will still be sufficient residual difference to operate the relay. For this protection to operate successfully, it is essential that the CTs all have identical characteristics so that the primary currents are accurately represented in the secondaries. In practice, this accuracy is difficult to achieve, especially where the measured currents are of greatly different values. This would not be such a problem with operation due to a fault on the bus, because the current in all of the connected circuits now feeding into the bus would be of a similar magnitude. However, in the case of a through fault, this CT unbalance or error current could cause inadvertent operation. You'll remember that we have discussed this in earlier videotapes. For example, if we have a heavy fault out here on line 4, the other 3 circuits will feed fault current into the bus and out along line 4 to the fault. We do not want the bus protection to operate under these circumstances, as it is an external fault. The actual current in line 4 is the sum of the currents in lines 1, 2, and 3. Where there are many more circuits connected to the bus, the difference could be much greater. Therefore, it is likely that the current in the CT secondaries will not accurately represent all the primary currents. This is especially true if the CT on line number 4 becomes saturated due to the heavy current flow. You'll remember we discussed saturation of the iron core in an earlier tape. This saturation curve shows that for current flows over 20 times rated, the secondary current is no longer in proportion to the primary. The secondary current on this saturated CT will be much lower than the sum of the secondary CTs 1, 2, and 3. The resulting imbalance would look like a bus fault and cause the relay to operate. This imbalance in secondary current is greatly exaggerated during the first 15 to 20 cycles of the fault. This is due to the transient that occurs in the primary current the moment it dramatically increases due to the fault. For example, this small sine wave represents the value of current under normal conditions. And here we see the same sine wave, but with much greater amplitude due to the fault on the line. Indeed, this may be high enough to cause saturation of the CT's iron core. However, there is yet another factor to make matters worse. Between normal current flow and stable fault current flow, a transient is created like this for perhaps 15 to 20 cycles. The amplitude of the current wave is the same as the stable fault current, but the whole sine wave has been raised as though a declining DC current has been injected into the circuit. This is known as the DC component, and its rate of decay actually depends upon the time constant, which in turn depends upon the resistance and reactance of the circuit. The nearer to the generator that the fault occurs, the higher the time constant and the slower the decay of this DC component. So what does this mean to our protection system? Well, the DC component causes the secondary current to actually decrease for the first few cycles. And this is when the primary current may still be rising to a very high level. Also, as we can see from this curve, the secondary current sine wave is badly distorted, which means that many harmonics are present. When harmonics are present in the protection system, this increases the likelihood of inadvertent relay operation. So now we have two factors resulting from saturation. A, the non-increase in secondary current as the primary exceeds the saturation point, usually about 20 times rated. And B, the reduction and distortion of secondary current due to the declining DC component of the transient fault current. All this means that for the first few cycles after initiation of the fault, the output of the heavily loaded CT will be most unreliable and will probably cause false tripping. As we shall see, there are several ways to get around this problem. The most simple is to use the delay of the time over current relay to ride through the transient period. A time delay of about 0.2 seconds, that is 12 cycles, is sufficient on most applications. But this may have to be increased if the bus is located close to a generator. The pickup current should be set so that it's above the estimated error current generated by the CTs for the through fault. This system is quite economical and is often used on low voltage buses. But you can see that it's slow and not very precise. More sophisticated arrangements are needed for protection of high voltage buses. One improved method uses directional relays fitted to every circuit connected to the bus. The operating contacts from the relays are all connected in series. When current flow is out of the bus, its respective relay contact is held open. Conversely, when current flow is into the bus, the contact is closed.
For a bus fault, current will flow into the bus from all circuits, and consequently, all of the contacts will be closed, energizing the relay to trip all of the breakers.
Where radial feeders are connected, there would be no reverse current into the bus, and therefore these are not included in the scheme. Although this protection scheme appears to be very simple, it has some disadvantages. First, because there are many contacts wired in series, the protection scheme could fail to operate due to one faulty pair of contacts. So careful maintenance is necessary with this system. Another problem is that the directional relay requires a polarizing source. If this is taken from a voltage transformer or the bus, the voltage may well fall close to zero during a bus fault, and therefore the directional relays would not operate. Another problem can result from weak sources, or sources that become weak during certain switching sequences. Now, at this point, before we start looking at more sophisticated bus differential protection, let's take a break. Please switch off the tape now and thoroughly review this material in your workbook. As we mentioned earlier, on large, high-voltage buses, a bus fault should be cleared as rapidly as possible due to the extremely high value of current which can flow into the fault. On the other hand, the last thing we want is for the bus to clear all of the breakers for a fault out on one of the connected circuits. What we need is high-speed differential protection which is reliable. Let's look once again at an example of simple current differential. There are 6 circuits connected to this bus with 300 amps entering on each of these lines 1 and 2 and 3. 500 amps flows out on line 4 and 200 amps out on line 5 and line 6. There will normally be a set of CTs and a differential relay for each individual phase. For good performance, all of the CTs must be of identical manufacture and the same ratio. For simplicity, we'll look at just one phase on each line. Let's assume this to be 100 to 1 for a rating of 500 amps primary. From this, we can easily calculate the magnitude of current and its direction of flow in each of the CT secondaries. As we would expect, in this case, the secondary currents cancel out. There is no current passing through the relay operating coil as the loads are balanced. Now, let's see what happens if a fault occurs on the bus with a magnitude of 18,000 amps. Now, we will have all 6 lines feeding current into the bus to supply the fault. Depending upon the reactance of each line from its respective source, the current flows will probably be similar. In this case, let's say 3,000 amps each. Now, in the secondary of each CT, we have 30 amps flowing. Note that this is 6 times the secondary rating of 5 amps, well within the range of accuracy. You'll remember that protection-type CTs retain 90% accuracy up to 20 times rated current. These secondary currents are all additive, so we have 180 amps passing through the relay operating coil. This will operate and trip all of the bus breakers. This is correct for an internal fault. Now, let's look at the case of a fault on line 4, fairly close to the breaker. As before, the fault magnitude is 18,000 amps. Lines 1, 2, 3, 5, and 6 will each feed 3,000 amps into the bus, and then 15,000 amps out along line 4 to supply the fault. Line 4 also feeds 3,000 amps to the fault. In the CT secondary, we have 30 amps on each of these lines and minus 150 amps on the faulty circuit. This would give us 0 current passing through the relay, so it will not operate. This is correct for an external fault. This is what we would like to see, but in practice, it does not happen like this. The problem lies with the different response by the CTs to the widely different current values. The level of current in this CT on the faulty line is 30 times its rating, so it is way over its saturation limit. Add to this the distortion occurring during the first few cycles, and it is likely that the secondary current will be, say, 110 amps instead of 150. So now we have a current of 40 amps passing through the operating coil of the relay, sufficient to cause a trip. This is incorrect operation. We do not want the bus protection to operate for external faults. One method to improve the reliability of operation during this transient period is to utilize a differential relay with multiple restraint coils. In the example shown, they would be connected like this. Applying the same numbers as before, we see that we have 40 amps passing through the relay operating coil, but this is opposed by the restraint coils. Let's look at these. Here, we have a total of 200 amps restraint in one direction, minus 60 in the other, so the total restraint is proportional to 140 amps. In this case, the percentage differential is the operating coil current, 40 amps, divided by the restraint current, 140, equals approximately 29%. So, in order to allow high-speed tripping and avoid misoperation during the first few cycles of the fault, we would need to set the percentage differential to about 40%. Multi-restraint bus differential relays are available with up to 6 restraint circuits. The relay is quite fast-acting. It operates within 50 to 100 milliseconds. That is approximately 3 to 6 cycles. Each bus circuit, which can provide a source of fault current, is connected to a separate restraint coil. On the other hand, CTs from radial feeders, which are not a source of fault current, are usually connected in parallel and then connected to one restraint coil. As there are no phase shift problems across a bus, the 3-phase CTs are normally connected in Y. In order to improve accuracy, it is important that the burden on CTs be kept as low as possible. Therefore, the CTs should not be used for any other purpose. For the same reason, the leads connecting the CTs should be of ample current carrying capacity. As all of the CT ratios are normally identical, the bus differential relays are not fitted with ratio taps. If a particular circuit does have a different CT ratio, then it's necessary to connect an auxiliary CT in order to match the others. Okay, so much for current differential. Another way of getting around the problem of CT saturation with bus protection is to use a different type of CT, one which has no iron core. The air core CT completely eliminates the problem of iron core saturation. This CT is known as a linear coupler. It looks similar to the conventional iron core CT, and it is often mounted in the circuit breaker bushings. The number of secondary turns are usually far greater than in the conventional CT to make up for the lack of iron and in order to provide the correct primary-secondary relationship. The linear coupler is usually designed to provide 5 volts on the secondary side for 1,000 amps passing through the primary. Note that the output of this type of CT is designated in volts instead of amps. The type of relay used is a voltage differential relay. For bus protection, the linear couplers are all connected in series like this. To simplify the example, let's say that we have 1,000 amps entering on each of these 2 lines, 1 and 2, and 1,000 amps leaving the bus in each of lines 3 and 4. So, on the linear coupler secondaries, we have plus 5 volts here, plus 5 volts here, minus 5 volts here, and minus 5 volts here. So the voltage differential relay sees 0 volts and will not operate. This is correct. For a fault on the bus, let's say 8,000 amps, each of the transmission lines will feed in 2,000 amps. We will now have a total of 40 volts across the relay operating coil, and the relay will trip. This is correct. For an external fault on one of the lines, we may have, say, 3,000 amps entering in each of the lines 1, 2, and 3, and 9,000 amps going to the fault on line 4. As the linear coupler does not suffer from saturation effects, the sum of the voltage will be 0. The relay will not trip for this external fault. This relay is highly sensitive and will trip in about 16 milliseconds, that is 1 cycle, so providing high-speed operation. In spite of these apparent advantages, this system is still not in wide use throughout the power industry. One problem is that it cannot use the conventional CTs, which are commonly purchased and stocked in large number for any utility company. Moreover, the linear couplers cannot be used for any other application within the system. And there is yet another bus differential scheme utilizing voltage relays instead of current relays. We'll be looking at this in the next segment. For now, please switch off the tape and review this material in your workbook. Another method of providing high-speed differential bus protection is by the use of high-impedance relays. Actually, this type of protection offers more than just high impedance, as we shall see. Let's go back to our simple current differential that we have already discussed. As we know, one major problem with this relay is that it may inadvertently trip for external faults due to the transient surge when the fault is initiated. In the high impedance differential relay, a resonant circuit is connected in series with the relay operating coil. This is a capacitor and reactor which are tuned to allow the passage of 60 hertz current only. It effectively filters out any harmonics and DC component due to wave distortion. One problem with this arrangement is that when the setting of the relay coil is adjusted, It changes the inductance in the circuit and so changes the resonant frequency. In order to avoid this, a rectifier is placed in the circuit so that only DC current is fed to the relay operating coil. Now, adjustment of the coil will in no way affect the inductance of the tuned circuit. The effect of the rectifier and the resonant circuit raises the total impedance across the relay at this point to quite a high value, usually around 2,500 ohms. This has another advantage. Note that this impedance is far, far greater than the impedance of the CTs, which is probably about 2 ohms or less. Therefore, any error current which exists as a result of saturation or different CT characteristics will flow through the CTs rather than through the high impedance relay circuit. To allow the correct distribution of this error current, it is important that the resistance in each of the CT branches should be equal and as low a value as possible up to the junction point. For this reason, the junction point will be located near to the CTs and at equal distance from each CT. The resistance of the connecting leads from the junction to the relay is not significant, as it is in series with the high impedance of the relay. When there is an internal fault on the bus, all of the circuits will feed into the bus, and therefore all of the secondary currents will be additive. In this situation, all of this current must flow through the differential relay and operate the tripping circuit. An out-of-balance current of, say, 20 amps flowing through the CT circuit of, say, 3 ohms would produce a voltage of 60 volts across the impedance relay. To trip for this condition, the relay would be set at 60 volts. However, this does raise another problem. Suppose under such conditions that the total secondary differential current is, say, 50 amps. If all of this current were to pass through the high impedance relay of 2,500 ohms, the total voltage drop across the relay would be 2,500 times 50 equals 125,000 volts. This would obviously destroy the relay. This problem is resolved by placing a parallel circuit across the relay so as to bypass most of the current. This bypass circuit is composed of a varistor, also known as a thyrite resistor, which has the property of decreasing its resistance as the voltage across it rises. This curve shows its characteristic. The effect on the differential relay is that as the voltage across the relay increases, more current is diverted through the varistor. This curve shows the comparison for a specific varistor. When voltage across the relay is 120 volts or lower, the current passing through the varistor branch is 0.01 amps. That is negligible. When this voltage reaches about 600 volts, all of the remaining current will be diverted through the varistor. Advantage is taken of this feature to provide further protection. An instantaneous overcurrent relay is installed in series with the varistor. This relay is set to operate instantaneously for very high levels of differential fault current. A range of pickup current settings are available from 2 amps and up. This is a plunger type relay which will trip within about 8 milliseconds, that is less than 1 cycle. This is extremely high-speed operation. The lighter bus faults will be cleared by the high impedance relay, and this operates within 20 milliseconds, that's about 1.5 cycles. This is also extremely fast operation. The setting of the high impedance relay is achieved by selecting the correct voltage tap, usually between 50 volts up to 500 volts. Let's look at an example to see how the relay's pickup value is determined. For an external fault, the CT in the faulted line may saturate, A voltage, which is the product of the current from the source CTs times the resistance of the windings and leads of the saturated CT, will be developed across the bus differential relay. Let's assume, for example, that the worst case or highest saturation voltage that could be presented to the relay was 100 volts. We would not want the relay to trip for this value. Therefore, we would desensitize the relay by setting it with a safety factor of 2 or 200 volts. The safety factor would have little effect on the relay's pickup for internal bus faults. Because of the importance of the bus in system operation, some installations include a supervisory circuit, which allows the operator to check the integrity of the bus differential protection circuit. This test circuit applies a low voltage to the relay circuit. When on standby, contact A is closed and 40 volts test voltage is available. Note that this is not sufficient to operate the high impedance relay. Contact B is closed to check for short circuits. A short in the CTs or the relay causes the voltage to fall. To check for open circuits, leave contact B closed and open contact A. The voltage should be 0. Check this one in your workbook. Okay, based on discussion of bus protection, I think it becomes quite clear that this type of protection does present a few special problems. First, because of its strategic position in the power system, any operation of bus protection relays will clear many circuits and probably cause a major system upset. For this reason, we do not want the bus protection scheme to operate unless there really is a fault on the bus. However, when there is a fault on the bus, it is important that the protection relays operate and clear the bus as soon as possible, preferably at high speed. The selection of CT ratings is particularly important because of the wide range of current flows which must be measured. And finally, because of the many factors involved, the selection of relay settings requires careful study and analysis. Make sure that you take the time to examine some of the bus protection schemes on your own power system. Check out the type of relays installed and the settings which are employed, and discuss this with your supervisor. At this point, please switch off the tape and thoroughly review this material in your workbook.